Part 1. Introduction to Quantum Physics and Paradoxes. Quantum physics is one of the most fascinating and mind-bending fields of science. It describes the strange behavior of particles at the smallest scales, where the laws of classical physics break down. In this introduction, we will explore why quantum mechanics is so strange, what paradoxes it creates, and how they challenge our understanding of reality. What is quantum physics? Quantum physics, also known as quantum mechanics, is the branch of physics that studies the behavior of matter and energy at the smallest scales, atoms and subatomic particles. Unlike classical physics, which follows predictable laws such as Newton's laws of motion, quantum physics operates on principles that seem almost magical. At the quantum level, particles can exist in multiple states at once, superposition. They can be connected across vast distances, entanglement. Their behavior changes when we observe them, the observer effect. They sometimes act like waves and sometimes like particles, wave-particle duality. These behaviors are not just theoretical ideas, they have been confirmed in countless experiments. However, they give rise to some of the most famous paradoxes in science. Why is quantum physics so strange? In our daily lives, we expect things to follow certain rules. If you throw a ball, it will travel in a predictable arc and land somewhere. If you turn on a light, you expect it to brighten the room. However, at the quantum level, things don't work this way. For example, a single particle can go through two different paths at the same time. A cat in a box can be both alive and dead until someone checks. Measuring a particle's state changes what it was before you looked. These effects sound like science fiction, but they have been repeatedly observed in scientific experiments. What is a quantum paradox? A paradox is a situation that contradicts common sense or logic. In quantum physics, paradoxes arise when the behavior of particles seems to defy the fundamental principles of reality. Some famous quantum paradoxes include Schrödinger's cat. A cat in a box is both alive and dead until observed. The Double-Slit Experiment. A particle can travel through two paths at once, but only if you aren't looking. Quantum entanglement. Two particles can instantly influence each other, no matter how far apart they are. The delayed choice experiment. A decision in the present can affect what happened in the past. Each of these paradoxes raises deep philosophical and scientific questions about the nature of reality, consciousness, and time. The origins of quantum physics. Quantum mechanics emerged in the early 20th century when scientists tried to explain phenomena that classical physics couldn't. Max Planck, 1900, discovered that energy comes in discrete packets called quanta. Albert Einstein, 1905, explained the photoelectric effect, showing that light can behave as particles. Niels Bohr, 1913, proposed the Bohr model of the atom, where electrons jump between energy levels. Erwin Schrödinger, 1926, developed the wave function equation that describes quantum behavior. Werner Heisenberg, 1927, introduced the uncertainty principle, stating that we can't know both the position and momentum of a particle simultaneously. These discoveries laid the foundation for quantum mechanics, but they also revealed the bizarre nature of the quantum world. The role of observation in quantum physics. One of the biggest mysteries in quantum mechanics is the role of the observer. Unlike classical physics, where objects exist independently of observation, quantum mechanics suggests that reality may not be real until it is observed. This idea comes from the famous Copenhagen interpretation, which states that particles exist in multiple states until measured. Before you look, they are in a superposition of all possible states. Once you observe them, they collapse into a single state. This raises deep questions. Does reality only exist when we observe it? What does this say about consciousness and the nature of existence? Could our observations shape reality itself? Why quantum paradoxes matter? Quantum paradoxes are not just weird thought experiments. They have real implications for science and technology. Many modern technologies rely on quantum mechanics, including computers and semiconductors. The behavior of electrons in microchips follows quantum principles. Lasers. The stimulated emission of photons is a quantum effect. Quantum computing, a new type of computing that could revolutionize processing power. Cryptography. Quantum encryption could create unbreakable security systems. Understanding quantum paradoxes helps us push the boundaries of knowledge and develop new technologies that could change the world. Coming up next, wave-particle duality and the double-slit experiment. Now that we have introduced quantum physics and its strange nature, we will explore one of the most famous quantum paradoxes, wave-particle duality. In the next section, we will discuss the nature of light and matter, how particles can behave like both waves and particles, the shocking results of the double-slit experiment. Stay tuned as we dive deeper into the mysteries of the quantum world. Part 2, Wave-Particle Duality and the Double-Slit Experiment. The mystery of wave-particle duality. One of the most fundamental paradoxes in quantum mechanics is wave-particle duality. It describes how light, electrons, and other particles can behave both as particles and as waves. In classical physics, waves and particles are distinct. A wave is something that spreads out and interferes with itself, like ripples in a pond. A particle is a tiny object that moves in a straight line, like a marble rolling on a table. But in quantum mechanics, things don't work that way. A single particle, such as an electron or a photon, can behave like a wave, spreading out and interfering with itself. This dual nature of particles is best demonstrated by one of the most famous experiments in history, the double-slit experiment. The double-slit experiment, a quantum mystery. The double-slit experiment is one of the most mind-boggling experiments ever conducted. It reveals the strange and paradoxical nature of reality at the quantum level. Step 1. Classical expectations. Imagine we set up a simple experiment. We have a barrier with two small slits in it. Behind the slits, we place a screen that detects particles. We shoot small objects like marbles toward the slits. What would we expect to see? If the objects are particles, they will go through one slit or the other, forming two distinct bands on the screen. If we use waves, like water waves, they will spread out, interfere, and create an interference pattern of multiple bands on the screen. So far, nothing surprising. This is just classical physics. Step 2. Electrons and photons behaving like waves. Now, let's replace the marbles with electrons, tiny quantum particles. We shoot electrons one at a time toward the slits. Since each electron is a particle, we would expect it to go through one slit or the other, forming two bands, just like the marbles. But that's not what happens. Instead, the electrons form an interference pattern, as if each electron is behaving like a wave and going through both slits at the same time, interfering with itself. This is impossible according to classical physics. It suggests that each electron is in multiple places at once, acting like a wave. Step 3. The observer effect. When we watch, reality changes. Now comes the truly bizarre part. What if we place a detector at the slits to see which slit the electron actually goes through? When we do this, the interference pattern disappears, and the electrons behave like normal particles, forming just two bands. In other words, when we observe the electrons, they choose to act like particles. But when we don't observe them, they act like waves. This means that the act of observation itself changes reality. This is known as the observer effect, one of the biggest mysteries in quantum mechanics. What does this mean for reality? The results of the double-slit experiment suggest some truly mind-blowing ideas. Particles exist in a superposition of states. Before we observe them, they are in multiple states at once. Reality changes based on observation. What we measure affects what is real. Consciousness may play a role in quantum mechanics. Some physicists speculate that the mind itself influences quantum states. This experiment has led to multiple interpretations of what quantum mechanics means for the nature of reality. Interpretations of the double-slit experiment. Scientists and philosophers have debated what this experiment means for over a century. There are several possible explanations. 1. The Copenhagen interpretation, Niels Bohr, 1927. This is the most widely accepted interpretation. It states that a quantum system exists in all possible states at once, superposition. When we measure it, the wave function collapses into a single reality. The act of observation determines the outcome. This interpretation suggests that reality is not definite until it is observed. 2. The many worlds interpretation, Hugh Everett, 1957. Everett proposed that, instead of the wave function collapsing, the universe splits into multiple realities. In one universe, the electron goes through the left slit, In another, it goes through the right. Every quantum event creates a new parallel universe. This means there are infinite versions of you, each living in a slightly different reality. Number 3. The pilot wave theory, Louis de Broglie, 1927. This theory suggests that particles always have definite positions. They are guided by an invisible pilot wave that determines their behavior. There is no wave function collapse. Everything is predetermined. This view tries to explain quantum mechanics without requiring an observer. The quantum measurement problem. The double-slit experiment leads to a huge problem in physics. Does reality only exist when we observe it? If we don't look at something, is it really there? Is consciousness required for the universe to exist? This is known as the quantum measurement problem. It challenges the idea that reality is objective and independent of observation. Some physicists believe that measurement is an interaction between a quantum system and its environment, while others argue that consciousness itself is required for measurement. Why this experiment is important. The double-slit experiment is not just a theoretical curiosity, it has major implications. Quantum computing uses superposition to perform calculations much faster than classical computers. Quantum cryptography uses quantum mechanics to create ultra-secure encryption. Quantum teleportation uses quantum entanglement to transfer information instantly. The nature of reality challenges our understanding of space, time, and consciousness. It also raises deep philosophical questions. Do we create reality just by looking at it? Is everything just probabilities until observed? Could the universe itself be a giant quantum system? What's next? Schrödinger's cat, the most famous quantum paradox. Now that we understand wave-particle duality and the observer effect, we will explore one of the most famous thought experiments in quantum mechanics, Schrödinger's cat, a paradox where a cat is both alive and dead at the same time. In the next section, we will cover how superposition works in real-world objects, the role of probability in quantum mechanics, what Schrödinger was really trying to say. Get ready for another mind-bending journey into the quantum world. Part 3. Schrödinger's cat, a cat that is both dead and alive. The thought experiment that broke reality. One of the most famous and mind-boggling paradoxes in quantum mechanics is Schrödinger's cat, a thought experiment proposed by Erwin Schrödinger in 1935. It was designed to illustrate the strange consequences of quantum mechanics when applied to everyday objects. The paradox challenges our understanding of reality by suggesting that a cat can be both alive and dead at the same time, at least until someone observes it. The setup, a quantum cat in a box. Imagine the following scenario. A cat is placed inside a sealed box. Inside the box, there is a radioactive atom that has a 50% chance of decaying within an hour. If the atom decays, it triggers a Geiger counter, which then releases poison gas, killing the cat. If the atom does not decay, the cat remains alive. Since quantum mechanics states that the atom exists in a superposition of decayed and not decayed states, the cat must also be in a superposition of being both dead and alive until we open the box and observe it. This means that before observation, the cat is both dead and alive at the same time. But the moment we check, the wave function collapses and the cat is found in only one state, either alive or dead. This concept is completely different from anything we experience in classical physics. It raises a deep question. Does reality only exist when we observe it? The superposition principle. How can the cat be both alive and dead? Schrödinger's cat is an example of quantum superposition, which means that a quantum system can exist in multiple states at once until it is measured. In quantum mechanics, particles do not have definite properties until they are observed. Instead, they exist in a probabilistic blur of possibilities. Mathematically, this is described using wave functions, pswas, which represent the probability of finding a system in different states. The wave function only collapses when a measurement is made. Thus, before opening the box, the cat is in a quantum superposition of both states. This means that before measurement, the cat is neither alive nor dead, it is both at the same time. Does this mean reality is not real? The paradox of Schrödinger's cat challenges our classical intuition about reality. If observation is necessary to determine an outcome, then does the universe exist independently of observers? This has led to several competing interpretations of quantum mechanics. 1. The Copenhagen interpretation, most popular. Proposed by Niels Bohr, this interpretation states that the cat is in a superposition of both states until the box is opened and observed. The act of observation collapses the wave function into a single reality. In this view, measurement creates reality. 2. The many worlds interpretation, Hugh Everett, 1957. This theory proposes that when we open the box, the universe splits into two parallel universes. In one universe, the cat is alive. In another universe, the cat is dead. These parallel universes exist independently and never interact. This means that every quantum event creates new, branching realities. Implication: if this is true, there are infinite versions of you, each living in different parallel worlds. Number 3. The objective collapse theories. Some scientists believe that wave function collapse happens spontaneously, not because of observation. This means that at some point, the superposition automatically collapses into a definite state. It suggests that quantum mechanics has an objective physical reality that does not depend on consciousness. Does this happen to real-world objects? Schrödinger's cat is a thought experiment, but could superposition happen to larger objects in real life? In the microscopic world, quantum effects like superposition are well documented. However, in the macroscopic world, we never see a coffee cup existing in two places at once. Why? There are two possible explanations. Decoherence. Large objects interact with their environment so much that their wave functions collapse very quickly. Hidden variables. Some physicists believe an unknown factor forces objects to behave classically. However, some experiments have shown that larger molecules, like buckyballs, can exhibit quantum superposition. In the future, scientists may be able to put entire living organisms into quantum states. How this affects quantum technologies. Schrödinger's cat may seem like a philosophical puzzle, but its implications are very real. Quantum mechanics is already being used in advanced technologies. 1. Quantum computing. In classical computers, bits can be either 0 or 1. In quantum computers, qubits can be 0, 1, or both at the same time, superposition. This allows quantum computers to solve problems exponentially faster than classical computers. 2. Quantum cryptography uses superposition and entanglement to create unbreakable encryption. Any attempt to intercept quantum information collapses the wave function, making eavesdropping impossible. 3. Quantum teleportation. Scientists have successfully teleported quantum states between particles using entanglement. This could lead to instantaneous communication over vast distances. What Schrödinger actually thought, ironically, Schrödinger did not believe in quantum superposition at a macroscopic level. He proposed the cat paradox to criticize the Copenhagen interpretation, arguing that it led to absurd conclusions. He wanted to show that applying quantum mechanics to real-world objects leads to paradoxes that must be resolved. However, modern experiments continue to confirm the strange reality of quantum mechanics. What's next? Quantum entanglement, the spooky connection between particles. Now that we understand superposition and the role of observation, we can explore an even weirder quantum paradox. Quantum entanglement, spooky action at a distance. In the next section, we will cover how two particles can be instantly connected across the universe, why Einstein called entanglement spooky action at a distance, how quantum entanglement is being used in teleportation and quantum internet. Part 4. Quantum entanglement, the spooky connection between particles. What is quantum entanglement? Quantum entanglement is one of the most mysterious and counterintuitive phenomena in physics. It describes how two or more particles can become linked in such a way that the state of one particle instantly determines the state of the other, no matter how far apart they are. This concept challenges classical physics because the effect seems to occur faster than the speed of light. Even Albert Einstein, who helped lay the foundations for quantum mechanics, was skeptical and famously referred to entanglement as spooky action at a distance. To understand why this phenomenon is so strange, let's start with a basic example. The EPR paradox, Einstein's challenge to quantum mechanics. In 1935, Albert Einstein, Boris Podolsky, and Nathan Rosen proposed a thought experiment known as the EPR paradox. They wanted to demonstrate that quantum mechanics was incomplete or flawed. The EPR argument was simple. Two particles can be created in such a way that their properties are correlated. If you measure one particle's property, such as spin or polarization, you instantly know the property of the second particle. This suggests that information is transmitted instantaneously between the two particles, violating the speed of light limit. Since faster-than-light communication is impossible according to relativity, Einstein and his colleagues believed that quantum mechanics must be missing some hidden variables that determine the outcome in advance. They concluded that quantum mechanics was an incomplete theory and that a deeper, classical explanation must exist. However, later experiments proved that Einstein was wrong. Entanglement is real, and it cannot be explained by hidden variables. How quantum entanglement works. To see why entanglement is so bizarre, let's consider a pair of entangled particles, A and B, created in a laboratory and sent to opposite ends of the universe. Each particle exists in a superposition of states, such as spin up and spin down. When an observer measures particle A, its wave function collapses into a definite state. Instantly, particle B also collapses into a corresponding state, even though no signal has traveled between them. This seems to suggest that the two particles are somehow communicating instantaneously, violating the laws of relativity. However, quantum mechanics does not allow for actual faster-than-light messaging. It only determines correlations between measurements. Bell's theorem, the proof that entanglement is real. In the 1960s, physicist John Bell developed a mathematical inequality to test whether quantum mechanics or hidden variable theories were correct. His work led to experimental tests that could determine if entanglement was a real, non-local effect or just an illusion. Bell's experiments involved measuring the properties of entangled particles in different orientations. According to classical physics, their correlations should obey certain limits. However, actual experiments violated Bell's inequality, proving that quantum entanglement is real. Hidden variable theories cannot explain the observed results. The universe is fundamentally non-local at a quantum level. Since then, countless experiments have confirmed Bell's findings, showing that entangled particles truly behave in a way that defies classical logic. Quantum teleportation, using entanglement for instant information transfer. One of the most exciting applications of entanglement is quantum teleportation. While it does not allow for faster-than-light travel or communication, it does enable the instantaneous transfer of quantum states. The process works as follows. Alice and Bob share a pair of entangled particles. Alice wants to send a quantum state to Bob without directly transmitting it. She performs a special joint measurement on her particle and the unknown quantum state. This causes Bob's entangled particle to instantaneously acquire the missing information, allowing him to reconstruct the original state. Quantum teleportation has already been demonstrated in laboratories over distances of hundreds of kilometers. In the future, it could lead to advanced quantum networks, enabling secure communication and powerful quantum computers. How entanglement is used in quantum technologies. Scientists are exploring multiple ways to harness entanglement for real-world applications. Some of the most promising uses include quantum cryptography. Entanglement allows for unbreakable encryption using quantum key distribution, QKD. If a hacker tries to intercept quantum keys, the entanglement is disturbed, immediately alerting both parties. Quantum Internet. Future Internet systems may rely on entangled quantum nodes to transmit information securely. Since entanglement cannot be intercepted or cloned, it could create a hacker-proof communication network. Super secure banking and data transfer. Banks and government institutions could use entanglement-based encryption for maximum security. Any attempt to eavesdrop on the data would destroy the entanglement, making hacking impossible. Advanced quantum sensors. Entanglement can enhance the precision of measurements, leading to ultra-sensitive quantum sensors. These sensors could revolutionize navigation, medical imaging, and even the detection of gravitational waves. Does entanglement prove that reality is an illusion? The philosophical implications of entanglement are profound. If two particles can remain connected across vast distances without any classical interaction, it raises fundamental questions about the nature of reality. Some interpretations suggest that entanglement may be evidence of a holographic universe, where space and time are emergent properties rather than fundamental. Others believe it hints at a deeper hidden structure of the cosmos, yet to be fully understood. Regardless of interpretation, one thing is certain: entanglement is real, and it challenges everything we thought we knew about how the universe works. What's next? The quantum Zeno effect, freezing reality with observation. Now that we have explored entanglement, the next paradox we will examine is the quantum Zeno effect, which suggests that the very act of observing a system can freeze it in place, preventing it from evolving. In the next section, we will cover how frequent observation can stop quantum decay, why measurement might control time at a microscopic level, the strange implications of freezing reality through consciousness. Part 5. The quantum Zeno effect, freezing reality with observation. The paradox of observation in quantum mechanics. One of the strangest consequences of quantum mechanics is that watching something can stop it from changing. This phenomenon is known as the quantum Zeno effect, named after the ancient Greek philosopher Zeno, who proposed paradoxes about motion and time. The effect suggests that a quantum system, such as an atom or a particle, cannot evolve if it is constantly measured. In other words, by simply observing something frequently enough, you can prevent it from decaying or changing states. This contradicts our everyday experience, where watching a process does not stop it from happening. Imagine looking at a melting ice cube and expecting it to freeze back just because you're staring at it. But in the quantum world, things behave very differently. How the quantum Zeno effect works. To understand this paradox, consider a radioactive atom. Normally, it will decay over time, emitting particles as it transforms into a more stable form. However, if a scientist continuously observes the atom at very short intervals, its decay process slows down or even stops entirely. Why does this happen? In quantum mechanics, particles exist in a superposition of states until measured. Each measurement resets the wave function, preventing the system from evolving naturally. As a result, frequent observations essentially freeze the quantum state in place. It's as if the universe doesn't allow change to occur when it's being watched too closely. The double-slit experiment and the role of observation. A similar mystery appears in the famous double-slit experiment, where particles like electrons or photons behave differently depending on whether they are observed. When not observed, particles act like waves, creating an interference pattern. When observed, particles behave like solid objects, following a single path. This suggests that measurement itself influences reality, supporting the idea that conscious observation plays a fundamental role in shaping the quantum world. Some scientists argue that this is just a property of quantum mechanics, not necessarily tied to human consciousness. However, the philosophical implications are enormous. If reality depends on observation, then how real is it when no one is looking? Quantum Zeno effect in real-life applications. While this effect may seem like a purely theoretical oddity, it has practical applications in modern technology. Quantum computing. Quantum computers rely on fragile quantum states, which must be protected from decoherence. The quantum Zeno effect can help stabilize quantum bits, qubits, making calculations more reliable. Medical imaging and quantum biology. Some biological systems, like enzymes and proteins, may use quantum effects to function. Understanding these effects could revolutionize medicine and biotechnology. Secure quantum communication. Quantum cryptography depends on measurement-based security. The quantum Zeno effect could be used to prevent data from being intercepted. Time control in quantum mechanics. Some researchers are exploring ways to manipulate quantum states using observation, potentially leading to new ways of controlling time at a microscopic level. Does the quantum Zeno effect mean we can control reality? If observation can freeze reality, does that mean we have control over the universe just by looking at it? While this may sound like science fiction, it raises deep philosophical and scientific questions. Is time an illusion? If measuring a system can stop its evolution, what does this say about time itself? Does consciousness play a role in shaping reality? If observation determines outcomes, then what is the true nature of the observer? Can this effect be harnessed for technology? Could we one day develop systems that halt decay or aging through controlled observation? These are some of the biggest mysteries in modern physics, and scientists are still searching for definitive answers. Part 6. The Double-Slit Experiment. The Paradox of Observation. The double-slit experiment is one of the most famous and baffling experiments in quantum mechanics. At first glance, it seems like a simple physics demonstration, but its results challenge our fundamental understanding of reality, observation, and even consciousness. This experiment is the key to understanding the strange behavior of quantum particles and how observation itself can change the outcome of events. Setting up the experiment. Imagine a simple setup. You have a barrier with two vertical slits cut into it. On the other side, there's a screen that records where particles land. Now, if we fire tiny particles, like electrons, or even larger objects like bullets, through the slits, what would we expect to see? In classical physics, if we shoot bullets through the slits, they will form two distinct patterns on the screen, directly behind each slit. This makes sense. Each bullet goes through one slit or the other, and lands in a predictable location. However, if we send a wave, like a water wave, toward the slits, something different happens. The wave will pass through both slits at once, creating an interference pattern on the screen. The peaks and troughs of the waves interact, reinforcing or canceling each other, forming a series of alternating bright and dark bands. Now, what happens when we perform this experiment with tiny particles like electrons or photons? Particles behaving like waves. Physicists expected electrons to behave like bullets, forming two distinct bands on the screen. However, when electrons were fired one by one through the slits, they did not behave like tiny solid objects. Instead, they created an interference pattern, just like waves. This meant that each individual electron somehow was going through both slits at the same time, interfering with itself as if it were a wave spread out over space. This is already strange, but things get even weirder. Scientists decided to place a detector at the slits to check which path each electron was taking. Were they splitting in two, passing through both slits, or were they somehow bouncing between slits? As soon as the electrons were observed, something shocking happened. The interference pattern disappeared, and the electrons behaved like tiny particles again, forming two distinct bands on the screen. This means that the mere act of measuring the electrons changed their behavior, as if the electrons knew they were being watched and adjusted accordingly. This is what makes the double-slit experiment so paradoxical. Observation itself alters reality. What does this mean? This experiment suggests something deeply unsettling. In the quantum world, a particle exists in a superposition of all possible paths until it is measured. Before observation, an electron doesn't have a definite position. It exists as a probability wave, capable of being in multiple places at once. But when we observe it, it chooses a definite state. This phenomenon is called wave function collapse, and it raises profound questions. Does reality exist independently of observation? Is consciousness playing a role in shaping reality? How do particles know they are being watched? Some interpretations of quantum mechanics, like the Copenhagen interpretation, suggest that quantum systems remain undefined until they are observed. Others, like the many worlds interpretation, propose that each possible outcome actually happens, but in separate branching universes. The quantum measurement problem. The double-slit experiment is at the heart of what is known as the measurement problem in quantum physics. It challenges our classical notion that reality exists in a definite state at all times. Instead, it suggests that quantum systems remain in a state of potentiality until an observer forces them to take on a definite form. Some physicists argue that observation doesn't necessarily require human consciousness. Any interaction with the environment could act as a measurement. But others speculate that consciousness itself plays a fundamental role in collapsing the wave function, linking quantum mechanics to theories of perception and reality. The bigger picture, why does this matter? The double-slit experiment is more than just a physics trick. It reveals the fundamental nature of reality. If observation truly influences the state of the universe, then reality may not be as solid and objective as we once thought. Instead, it might be a dynamic, interconnected system where the observer is not separate from the observed, but an active participant in shaping the universe. This mind-bending conclusion has led to some of the most profound discussions in physics, philosophy, and even consciousness studies. Is the universe waiting to be observed? Do we, as conscious beings, play a role in creating reality? The implications are staggering, and physicists are still trying to unravel this mystery. But one thing is clear. The double-slit experiment is a paradox that challenges everything we know about the nature of existence. Part 7. The measurement problem. Does reality exist without observation? What does it mean to observe reality? In our everyday world, things exist whether we look at them or not. A tree stands in the forest even if no one is around to see it. A book on your desk remains there, unchanged, whether you're looking at it or not. But in the quantum world, things are not so simple. Before being observed, particles exist in a state of superposition, meaning they have multiple possible properties at the same time. But the moment we observe them, they choose one reality. This is the heart of the measurement problem in quantum physics. Does reality exist in a definite state when it is not being observed? Or does observation itself create reality? This paradox shakes the foundations of our understanding of the universe. The observer effect, how observation changes reality. One of the biggest mysteries in quantum physics is that the act of measurement changes the state of a quantum system. Before measurement, a quantum particle, like an electron or photon, exists in a superposition of multiple states. The moment it is observed, the wave function collapses into a single definite state. This means that observation isn't just a passive action, it actively shapes reality. This strange effect has been confirmed in multiple experiments, including the famous double-slit experiment, where the mere act of measuring a particle's path changes its behavior. But why does this happen? What is it about measurement that forces reality to make a choice? The Copenhagen interpretation, reality is undefined until measured. The dominant explanation for the measurement problem comes from the Copenhagen interpretation, proposed by Niels Bohr and Werner Heisenberg in the 1920s. According to this view, a quantum system exists in all possible states simultaneously, superposition, until it is measured. The act of measurement forces the system to take on a single, definite state. Before measurement, the system is described by a wave function, a mathematical representation of all its possible states. This means that reality does not exist in a definite form until it is observed. This idea is deeply unsettling. It suggests that the universe at a fundamental level is not solid or objective, but is instead probabilistic and undefined until someone looks at it. But why should human observation matter? Why does the universe seem to care whether it is being watched? Does consciousness create reality? Some physicists and philosophers argue that the measurement problem suggests consciousness plays a fundamental role in shaping reality. If a quantum system only chooses a state when measured, then does the mind of the observer somehow influence the outcome? Could our awareness be what collapses the wave function into a definite reality? This idea is known as the von Neumann-Wigner interpretation, which suggests that consciousness is not separate from the physical universe. The act of conscious observation creates the reality we experience. This idea, while fascinating, is highly controversial. It raises deep questions about the relationship between mind and matter, but it lacks definitive experimental proof. Alternative explanations. Is there a hidden mechanism? Not all physicists agree that consciousness has anything to do with wave function collapse. Several alternative explanations attempt to solve the measurement problem. Decoherence theory. The environment causes collapse. Instead of human observation, the collapse of the wave function could be caused by interaction with the environment. As soon as a quantum system interacts with particles in the surrounding world, it chooses a state. This means that measurement is just another form of interaction, not something special. The many worlds interpretation, no collapse, just splitting. According to this view, the wave function never collapses. Instead, every possible outcome happens, but in different parallel universes. If you measure a quantum particle and see one result, another version of you in a parallel universe sees a different result. Bohmian mechanics, hidden variables guide reality. Proposed by David Bohm, this interpretation suggests that quantum particles have hidden properties that determine their behavior. These hidden variables exist outside of what we can currently measure. If true, quantum mechanics would just be an incomplete theory rather than a fundamentally strange one. These interpretations show how deeply unresolved the measurement problem remains. Schrödinger's cat, the ultimate paradox of measurement. One of the best ways to illustrate the measurement problem is through the famous thought experiment of Schrödinger's cat. Imagine a cat inside a sealed box with a quantum mechanism that has a 50% chance of releasing poison. According to quantum mechanics, before opening the box, the cat is both alive and dead at the same time, a superposition of states. The moment you open the box to check, the wave function collapses, and the cat becomes either fully alive or fully dead. But what was the cat before the box was opened? Was it really in both states, or did it always have a definite reality that we just didn't know about? This paradox directly illustrates the weirdness of quantum measurement. Does observation truly determine the outcome, or does reality exist independently and we just don't understand how? Quantum mechanics and free will, are we just part of a larger system? The measurement problem also has philosophical consequences. If reality doesn't take shape until it's observed, then does that mean the choices we make are determined by quantum mechanics? Or is our free will somehow influencing the quantum world? Some researchers believe that understanding the measurement problem could help unlock the secrets of consciousness itself. Modern experiments and the future of quantum measurement. Scientists are still searching for definitive answers about measurement. Quantum delayed choice experiments. These experiments suggest that a choice made in the present can change the past at the quantum level. This implies that the universe is nonlinear and cause and effect may not work the way we think. Quantum computers and wave function collapse. Quantum computers rely on superposition to perform calculations. Understanding measurement could help harness quantum effects for new technologies. Testing consciousness in quantum mechanics. Some studies try to test whether human observation actually influences quantum states. If consciousness plays a role, this could revolutionize our understanding of reality and the mind. What's next? The many worlds interpretation, infinite universes from one choice. Now that we've explored the mystery of quantum measurement, the next big paradox takes us even further. What if every possible quantum outcome actually happens? What if reality does not collapse at all, but instead splits into countless parallel universes? In the next section, we will explore the many worlds interpretation, a mind-bending theory that suggests we live in an infinite multiverse where every choice spawns a new reality. Part 8. The many worlds interpretation, infinite universes from one choice. What if every decision creates a new universe? Imagine you are faced with a simple choice, to take a sip of coffee or tea. According to classical physics, you make a decision, and reality follows a single path. But what if, at that exact moment, the universe splits into two versions, one where you drink coffee and another where you drink tea? This is the foundation of the many worlds interpretation, MDI, of quantum mechanics, first proposed by Hugh Everett III in 1957. It suggests that every time a quantum event occurs, the universe branches into multiple versions, each representing a different possible outcome. If true, this means every possible outcome of every quantum event actually happens, just in a different universe. There are infinite versions of you, each living out different possibilities. The universe is not collapsing into a single state, but constantly branching into new ones. Could this theory mean that there are countless alternate versions of reality, each as real as the one you are experiencing right now? The quantum origins of the many worlds interpretation. The many worlds interpretation comes from an alternative way of solving the measurement problem in quantum mechanics. In the standard Copenhagen interpretation, the wave function collapses when measured, forcing reality to choose a single state. But the many worlds interpretation rejects this idea completely. Instead, it proposes that the wave function never collapses. Instead of one outcome happening and others disappearing, all outcomes happen, but in separate, non-interacting universes. Every quantum event results in a branching of reality, leading to a near-infinite number of parallel worlds. In other words, the universe is constantly splitting into different versions of itself. How many worlds are there? If the many worlds interpretation is correct, then every quantum interaction down to the movement of a single electron, creates a new branch of reality. Since quantum interactions happen constantly, the number of universes is exponentially increasing with every moment, possibly infinite, meaning every possible version of history exists somewhere. If you chose a different career, ended up in a different city, or even had a different personality, there's a universe where each of these things happened. This means there could be a universe where you are a billionaire, a universe where dinosaurs never went extinct, a universe where Earth never formed at all. Every possibility exists in its own branch of reality. Schrödinger's cat and the many worlds interpretation. In Schrödinger's cat experiment, a cat inside a box is both alive and dead in a superposition until observed. According to the many worlds interpretation, when you open the box, the universe splits into two realities, one where the cat is alive and another where it is dead. You do not collapse the wave function. Instead, you simply find yourself in one of the two possible worlds. In the other universe, another version of you observes the opposite outcome. This means that every quantum measurement results in multiple realities rather than a single definite outcome. Is there a way to prove many worlds? The problem with the many worlds interpretation is that we cannot directly observe other universes. They are separate from our own. However, some theoretical tests might hint at its validity. Quantum interference experiments. If the wave function truly never collapses, then quantum interference patterns could reveal subtle evidence of other branches of reality. Quantum computing and parallel processing. Some physicists speculate that quantum computers work by performing calculations across multiple universes at once. If true, this could provide indirect evidence for the many worlds interpretation. Delayed choice and quantum erasure experiments. These experiments suggest that choices made in the present can influence past quantum events, which might be better explained if all outcomes exist simultaneously in different universes. While direct proof remains elusive, many worlds remains one of the most intriguing explanations for quantum mechanics. Philosophical and scientific implications of many worlds. If the many worlds interpretation is correct, it radically changes our understanding of reality, free will, and determinism. Every possible decision you could make already happens in some branch of reality. This suggests that everything that can happen does happen somewhere. The nature of identity. If there are infinite versions of you living different lives, which one is the real you? Could consciousness exist across multiple realities simultaneously? The future of science and technology. If we could somehow communicate with other universes, it would revolutionize computing, physics, and even human existence. Could quantum mechanics one day allow us to travel between alternate realities? Does many worlds solve the measurement problem? Many worlds avoids the problem of wave function collapse by simply eliminating it. There is no collapse, only branching. But this raises new questions. Why do we only experience one reality instead of seeing all branches? If infinite versions of us exist, why do we feel like we are only in one world? Some physicists propose that our consciousness only follows one timeline. But whether that is a fundamental rule or just an illusion remains unknown. Popular culture and the many worlds idea. The idea of parallel universes has fascinated both scientists and storytellers. Science fiction and movies often explore the idea of alternate realities where different versions of history play out. Films like Interstellar, Everything Everywhere All at Once, and The Matrix draw inspiration from many worlds theory. The idea that every choice creates a new reality has inspired endless speculation about what could be happening in the other versions of our lives. What's next? The delayed choice experiment. Does the future affect the past? Now that we've explored the possibility that every decision creates a new universe, an even stranger question arises. Could choices made in the present influence the past? The next section will explore the delayed choice experiment, a mind-bending quantum test. Time and causality in quantum mechanics. Can future observations change past events? The strange idea that the universe is not set in stone, but shaped by choices across time. Part 9. The delayed choice experiment. Does the future affect the past? Quantum physics is strange. So strange that the very laws governing reality seem to bend when observed at the most fundamental level. One of the most perplexing aspects of quantum physics involves the delayed choice experiment. This thought experiment, first proposed by physicist John Archibald Wheeler in 1978, challenges our traditional understanding of time, causality, and the very nature of reality itself. In essence, the delayed choice experiment examines the idea of whether decisions made in the present can influence events that have already occurred in the past. At the heart of this idea is the concept of wave-particle duality, a fundamental principle in quantum mechanics. This experiment pushes the boundaries of our perception of time, raising the question, can our choices in the present affect the past? The setup of the delayed choice experiment. To understand the implications of the delayed choice experiment, let's first look at how it's set up. Wheeler's original thought experiment involved a light source, a beam splitter, two detectors, and a decision point that is delayed. The light source emits a photon, which then travels toward a beam splitter. The beam splitter has the ability to send the photon in one of two possible directions, to detector A or to detector B. What makes this experiment delayed is that the decision about which path the photon will take is not made until after the photon has already passed the beam splitter. In other words, the choice of whether to observe the photon as a particle or a wave is not made until after the photon has already entered the apparatus, potentially causing the photon to behave differently depending on whether it's observed or not. Wave-particle duality and the role of observation. To grasp why this is mind-bending, we need to understand wave-particle duality. Quantum objects, like photons, do not behave strictly as particles or waves. Instead, they exhibit properties of both depending on how they are observed. When not being observed, a photon behaves like a wave, existing in a superposition of all possible states. When observed, however, it collapses into a single particle, behaving in a predictable, localized manner. In the delayed choice experiment, the behavior of the photon depends on whether or not the observer, or measurement device, is set up to detect it as a wave or a particle. If the photon is observed as a wave, it creates an interference pattern as the wave passes through both slits in the beam splitter and interferes with itself. If the photon is observed as a particle, it will behave like a localized object and will not produce an interference pattern. Here's where things get weird. The decision about whether the photon will act like a wave or a particle is made after the photon has already passed through the beam splitter and is on its way to one of the detectors. Yet, the result of the experiment, whether the photon behaves as a wave or as a particle, seems to depend on the measurement made at the very end of the experiment. This means that the photon's behavior seems to be affected by decisions made after the photon has already passed through the beam splitter. In a sense, the future, the decision to measure the photon, is influencing the past, the photon's behavior as it passes through the apparatus. The implication of backwards causality. Wheeler's delayed choice experiment introduces the concept of what is called backwards causality. In classical physics, we think of cause and effect as flowing in one direction, from the past to the future. A cause happens first, and the effect follows afterward. But in the quantum realm, the idea of causality begins to break down. In the case of the delayed choice experiment, it seems that the future, the observer's decision, can reach back and affect the past, the photon's behavior, before the measurement. This challenges our fundamental understanding of time and the flow of events. If the future can influence the past in quantum experiments, then perhaps the distinction between past, present, and future is not as clear-cut as we've always believed. This idea leads us to question, what is the true nature of time? Is time just an illusion, a construct of the human mind, or does it behave differently at the quantum level? The experiment in practice. Though Wheeler's original thought experiment was purely theoretical, experimental physicists have since devised ways to test its predictions. In 1999, physicist Yoon-Ho Kim and his team at the University of Maryland conducted an experiment that provided strong evidence for the concept of delayed choice. The experiment used a setup similar to Wheeler's, with a photon passing through a beam splitter and the decision about how to measure it being made after the photon had passed through. Their results confirmed that the photon's behavior did indeed depend on the decision made after it had already passed through the beam splitter. The photon seemed to know what kind of measurement was going to be made, and it adapted its behavior accordingly, even though the decision about the measurement was made in the future. This experiment suggests that the photon's behavior is not strictly determined at the moment it passes through the beam splitter. Instead, it appears to be influenced by the future decision, adding weight to the idea of quantum systems having no definite state until they are measured. Does the future affect the past? The delayed choice experiment forces us to reconsider our understanding of time and causality. If the future can influence the past, as the results of this experiment suggest, then what does that mean for our understanding of the world around us? Does this imply that the flow of time is not as linear as we perceive it to be? Could the future be somehow connected to the past in a way we have yet to fully comprehend? One interpretation of this phenomenon is that the act of observation in quantum mechanics is not just a passive event, but an active force that determines the behavior of particles. The decision made by the observer, the measurement of the photon, influences the outcome of events, even if the measurement is made in the future. The act of observation, in a way, creates reality. This raises profound philosophical questions. If our choices in the present can affect past events, do we have the ability to shape reality in ways that extend beyond our immediate time and space? Is there some deeper connection between the observer and the observed, bridging the gap between the future and the past? These questions may seem like science fiction, but they are rooted in the real, observable results of quantum experiments. Quantum mechanics and the nature of reality. The delayed choice experiment forces us to confront the fundamental nature of reality. It suggests that the universe at its core is not a deterministic, clock-like mechanism that follows a predictable path. Instead, it points to a reality that is dynamic, flexible, and deeply interconnected. In the quantum world, the future and past may not be as separate as we once thought. This experiment highlights one of the most startling features of quantum mechanics, the observer's role in shaping reality. It suggests that reality is not set in stone, but rather is influenced by the act of observation. The universe, it seems, may not exist in the way we assume until it is measured. Until that moment, particles exist in a superposition of states, able to be in multiple places at once, behaving as both waves and particles simultaneously. Conclusion: a new view of time and causality. The delayed choice experiment is a key part of the strange, often paradoxical nature of quantum physics. It challenges our most basic assumptions about the flow of time, causality, and the role of the observer. By showing that the future can influence the past, it invites us to reconsider our place in the universe. The very fabric of reality appears to be more malleable than we ever imagined, with time, space, and causality all interconnected in ways that defy our intuition. As we delve deeper into the mysteries of quantum mechanics, we are reminded that our understanding of the universe is still in its infancy. The delayed choice experiment forces us to confront the possibility that our perception of time, reality, and causality may need to be rewritten entirely. Is the future influencing the past? Quantum physics says, maybe. And in doing so, it opens up an entirely new way of thinking about the world around us, inviting us to embrace the strange and unpredictable nature of reality. Part 10. Quantum Tunneling. The Impossible Jump. Quantum physics is full of bizarre phenomena, but one of the most mind-blowing and counterintuitive is quantum tunneling. Imagine trying to pass through a solid wall, something that seems utterly impossible, right? Now, in the quantum world, particles can do just that. They can tunnel through barriers that would otherwise be insurmountable in the classical world of everyday physics. This seemingly impossible jump raises a number of questions about the nature of reality, space, and time. What is quantum tunneling? At the heart of quantum tunneling is the wave-particle duality we discussed earlier. In classical physics, if an object doesn't have enough energy to overcome a barrier, it can't pass through it. For instance, if a ball is rolling toward a hill, but it doesn't have enough speed to reach the top, it will simply stop at the base. No matter what, the ball cannot pass over the hill unless it has enough energy to reach the peak. However, in the quantum realm, things work quite differently. Subatomic particles, like electrons, don't have definite locations and speeds until they are observed. Instead, they exist in a cloud of probabilities, represented by a wave function. This means that an electron doesn't just have a single position, it has a range of possible positions that it could occupy, each with a certain probability. Now, here's where quantum tunneling comes into play. When a particle encounters a barrier, there's a chance that it might tunnel through the barrier, even if it doesn't have enough energy to surpass it, according to classical physics. The particle doesn't go over the barrier, it goes through it, as if the barrier itself didn't exist. How does tunneling happen? To understand tunneling, let's visualize it in terms of a potential energy barrier. In the classical world, a particle, like an electron, will encounter a wall or barrier, and if the particle doesn't have enough energy, it will simply bounce back. But in quantum mechanics, the situation is different. Instead of a solid, impenetrable wall, the barrier becomes a region where the probability of finding the particle drops to zero. But, and this is the key point, it never drops to absolute zero. It just gets extremely small. Because of this, there is a very small but non-zero chance that the particle will tunnel through the barrier, even though it doesn't have enough energy to go over it. This phenomenon can be visualized as the wave function of the particle spreading out across space. When the wave encounters a barrier, part of the wave leaks through the other side of the barrier. This leakage is what allows the particle to appear on the other side of the barrier, even though classical physics would say it shouldn't be able to get through. The role of probability. Quantum tunneling is fundamentally a probabilistic event. The key idea here is that before we observe or measure the particle, we can't say exactly where it is, only where it is likely to be. The particle's wave function spreads out over space, meaning that it has a probability of being in many locations at once. When it encounters a barrier, the wave function extends beyond the barrier, and the particle has a small but non-zero probability of being found on the other side. The probability decreases exponentially with the thickness of the barrier and the particle's energy, but as long as there is some non-zero probability, the particle may end up on the other side of the barrier. Real-world applications of quantum tunneling. While quantum tunneling might sound like a wild, theoretical concept, it has real-world applications that are crucial to modern technology. One of the most famous examples is in the operation of semiconductor devices, which are the backbone of modern electronics. In devices like tunnel diodes and microchips, quantum tunneling plays an essential role in their functioning. In a tunnel diode, for instance, electrons can tunnel through a potential barrier in the semiconductor material, allowing current to flow even when classical physics would predict that no current should pass. Another example is the process of nuclear fusion that powers the sun. In the sun's core, protons are moving so fast that they should, in principle, repel each other due to their positive charges. However, the temperature and pressure inside the sun are so extreme that the protons have a very small chance of tunneling through the repulsive electrostatic barrier and fusing together. This process, called quantum tunneling, is responsible for the energy produced by the sun. Tunneling is also used in devices like scanning tunneling microscopes, which allow scientists to observe individual atoms by using tunneling currents to detect the position of electrons at the atomic scale. Quantum tunneling and the nature of reality. Quantum tunneling is not just a fascinating phenomenon. It's also a reminder that the universe doesn't behave the way we intuitively think it should. In the macroscopic world, things follow predictable classical rules, and objects can't pass through walls. But at the quantum level, the rules are radically different. Tunneling challenges our understanding of space and time, and it shows us that what seems impossible in one context may be completely normal in another. This paradox raises deeper questions about the nature of reality itself. If particles can pass through barriers, does that imply that there are no true boundaries in the universe, only regions of probability and potential? Could there be other phenomena, like tunneling through time or dimensions, that we haven't yet discovered? Some theorists have even speculated that the idea of quantum tunneling might explain some of the more mystical aspects of the universe, such as consciousness and the so-called multiverse. the idea that multiple realities or timelines may exist simultaneously. Quantum mechanics offers us a glimpse into a world where the impossible is not only possible, but also essential to understanding the true nature of the universe. Quantum tunneling and the future of technology. Looking to the future, quantum tunneling has the potential to revolutionize technology in ways that we can barely imagine today. For instance, researchers are exploring the possibilities of quantum computers, which could use quantum tunneling to perform calculations exponentially faster than classical computers. Quantum tunneling could also play a role in the development of more efficient solar panels. By harnessing the unique properties of tunneling, we could create materials that allow for better energy absorption and conversion, potentially leading to more sustainable and powerful energy sources. In medicine, tunneling might even have applications in nanotechnology, allowing for the creation of more precise and efficient medical devices, including drug delivery systems that can target specific cells and tissues within the body. As we continue to explore the strange and fascinating world of quantum mechanics, the potential applications of quantum tunneling are bound to expand, pushing the boundaries of what we think is possible and opening up new frontiers in technology and science. Conclusion: the impossible is possible. Quantum tunneling teaches us that at the smallest scales of the universe, the impossible is possible. Things we would never imagine happening in the classical world, like particles passing through barriers, are routine occurrences in the quantum realm. This phenomenon challenges our understanding of reality and reminds us that the universe is much stranger and more complex than we could have ever imagined. The idea that a particle can simply jump through a barrier that should be impassable is both fascinating and unsettling. It forces us to confront the limitations of our understanding of the physical world and consider the possibility that the fundamental laws of nature may be far more fluid and flexible than we previously thought. In quantum mechanics, the universe is not a rigid, predictable place. It is a realm where the impossible becomes possible, and where particles and waves exist in a world of probability, uncertainty, and wonder. Part 11. Quantum superposition, being in two places at once. Quantum superposition is one of the most bizarre and fundamental principles of quantum mechanics. It challenges our classical understanding of reality by suggesting that particles can exist in multiple states or locations simultaneously until they are observed. This mind-bending concept lies at the heart of quantum mechanics and has profound implications for our understanding of the universe. The strange nature of superposition. In classical physics, an object is always in a definite state. A car is either parked in one spot or another, but never in two places at once. A light switch is either on or off. However, in the quantum world, particles such as electrons and photons do not behave this way. Instead, quantum particles exist in a superposition of all possible states at the same time. It is only when they are measured or observed that they collapse into a single definite state. This means that, until observed, a particle is in multiple locations, has multiple energies, or can be spinning in different directions simultaneously. The classic thought experiment, Schrödinger's cat. One of the most famous illustrations of quantum superposition is Schrödinger's cat, a thought experiment proposed by physicist Erwin Schrödinger in 1935 to highlight the paradoxes of quantum mechanics. Imagine a cat placed inside a sealed box. Inside the box, there is a radioactive atom that has a 50% chance of decaying within an hour. If it decays, it triggers a mechanism that releases poison, killing the cat. If the atom does not decay, the cat remains alive. Quantum mechanics suggests that until we open the box and observe the cat, it is in a superposition of both alive and dead states at the same time. Only when we look inside does the cat state collapse into either alive or dead. This paradox illustrates how strange and counterintuitive quantum superposition is when applied to the macroscopic world. Experimental proof of superposition. Superposition is not just a theoretical idea. It has been experimentally confirmed in multiple ways. One of the most famous demonstrations comes from the Double-Slit Experiment. When electrons or photons are sent through two slits, they behave as if they pass through both slits at once, creating an interference pattern. However, if we place a detector to observe which slit they go through, the interference pattern disappears, and they behave like classical particles. Another experiment that confirms superposition is conducted with quantum bits, or qubits, used in quantum computing. Unlike classical bits, which can be either 0 or 1, qubits can be both 0 and 1 simultaneously due to superposition. This is what gives quantum computers their incredible computational power. The role of observation. One of the most puzzling aspects of quantum superposition is that observation appears to determine reality. Before measurement, a particle exists in all possible states at once, but the moment we observe it, it chooses one definite state. This is known as wave function collapse and remains one of the greatest mysteries of quantum mechanics. Some interpretations suggest that observation itself causes the collapse, while others, like the many worlds interpretation, propose that all possible outcomes occur, but in separate parallel universes. Implications of superposition. Quantum superposition has real-world applications and is revolutionizing technology. Some key implications include quantum computing. Superposition allows qubits to perform multiple calculations at once, making quantum computers exponentially more powerful than classical computers. Quantum cryptography. Superposition plays a role in securing information through quantum encryption methods, which could lead to virtually unbreakable security. Quantum teleportation. Superposition is crucial in experiments involving quantum teleportation, where the state of a particle can be transmitted over long distances. Understanding reality. Superposition raises philosophical questions about the nature of existence and whether reality is fundamentally probabilistic rather than deterministic. Conclusion. Quantum superposition is one of the most perplexing and fascinating concepts in physics. It challenges our classical view of the world, suggesting that particles can exist in multiple states until observed. The fact that observation influences reality at the quantum level forces us to rethink the nature of existence itself. As scientists continue to explore and harness quantum superposition, we are on the verge of unlocking new technologies and deeper insights into the fabric of the universe. But for now, one thing is clear. In the quantum realm, reality is far stranger than we ever imagined. Part 12. Conclusion. How quantum physics challenges our understanding of reality. Quantum physics isn't just a branch of science, it's a complete shift in how we perceive the universe. For centuries, we believed in a deterministic world governed by predictable laws, where things happen in clear, logical sequences. But quantum physics upends this idea, showing us a reality that is strange, fluid, and full of paradoxes. It pushes the boundaries of our imagination and forces us to reconsider everything we thought we knew about the universe, existence, and even ourselves. Rewriting the rules of reality. From wave-particle duality to quantum entanglement, the concepts we've discussed throughout this video represent the most fundamental ways in which quantum mechanics challenges our conventional understanding of reality. The very fabric of the universe is far stranger than we could have ever imagined. Quantum physics reveals that, at the most fundamental level, particles don't behave like little balls zipping around a predictable path. Instead, they exist in a haze of probabilities, their behavior shaped by the act of observation itself. Matter can be in multiple places at once, and the future can affect the past. Some particles can even pass through barriers that classical physics says should be insurmountable. Perhaps most unsettling of all is the idea that reality, as we experience it, is not fixed. It's not a set of laws and certainties, but rather a fluid, ever-changing tapestry where uncertainty and probability reign. The universe, at its core, is not as solid and predictable as we might like to think. The observer's role in shaping reality. One of the most profound implications of quantum mechanics is the idea that our observation of the universe plays a crucial role in shaping it. The very act of measurement, whether we're looking at the behavior of a tiny particle or studying the vast reaches of space, seems to influence the outcome. This suggests that reality is not just a passive stage where events unfold, it's a dynamic and interactive process in which we are active participants. This role of the observer challenges the classical view that reality exists independently of us. In the quantum world, reality might not exist in a definite state until we measure it, and by simply observing the world, we can alter its course. This gives rise to fundamental questions about consciousness, perception, and the relationship between the observer and the observed. It leads us to wonder, is reality a creation of our minds, or is there something deeper at play? The philosophical and existential implications. Beyond its scientific implications, quantum mechanics also forces us to confront deep philosophical questions. Does the nature of reality exist independently of us, or is it shaped by our consciousness? If the universe is not deterministic, do we have true free will, or is everything simply a result of probabilities? Quantum mechanics touches on the very nature of existence. The idea that the universe is made up of particles that behave in unpredictable, probabilistic ways makes us question the essence of everything around us. Is reality fixed, or is it in constant flux, shaped by forces we don't fully understand? And perhaps most importantly, what does this mean for our place in the universe? The concept of parallel universes and multiple realities emerging from the choices we make further deepens these questions. Could there be infinite versions of ourselves living out different versions of our lives in different realities? Are we just one manifestation of an infinite number of possibilities? These are questions that go beyond the realm of physics and into the domain of philosophy, and they challenge our understanding of who we are and what it means to exist. The future of quantum physics. As strange and difficult as quantum mechanics may seem, it holds the key to countless breakthroughs in science and technology. From quantum computing to quantum communication and cryptography, the principles of quantum mechanics have already begun to revolutionize our technological landscape. In the future, quantum physics may allow us to tap into new forms of energy, build more powerful computers, and even discover new realms of space and time. But perhaps more importantly, quantum physics challenges us to think about the nature of the universe in entirely new ways. It invites us to explore the limits of human knowledge and imagination, pushing us to rethink the very building blocks of reality. The deeper we probe into the quantum world, the more we realize that the universe is far stranger, more complex, and more mysterious than we could have ever imagined. Conclusion: a universe of possibilities. Quantum physics doesn't just change our understanding of particles and waves, it changes our understanding of everything. It forces us to reconsider the nature of reality itself, showing us that the universe is full of uncertainty, possibility, and wonder. It teaches us that our perception of reality is limited, and that there may be more to existence than meets the eye. The paradoxes we've explored, wave-particle duality, quantum entanglement, the delayed choice experiment, are not just mind-bending concepts. They are windows into a deeper reality, one that transcends the boundaries of classical physics and invites us to think beyond what we know. Quantum mechanics challenges us to let go of our assumptions and embrace the mysteries of the universe, to accept that there is more to reality than meets the eye. In the end, quantum physics shows us that the universe is not just a place we live in, it's a place we are a part of, a place we help create with every observation, every choice, and every question we ask. The world of quantum physics is full of mysteries, and perhaps the greatest mystery of all is the way it invites us to discover not just the world, but also ourselves.